the previous talks, I think that the topic of social intelligence in human and robots is really taking a new turn. The advances in LLMs, in deep learning, are completely changing the way we're looking into the problem, and it's really an exciting time to be working on those topics. First things first, I want to acknowledge the contribution of the European Union. This work has been funded by several projects, in particular Perseus and Arise, that are ongoing projects funded by the EU. Yes, so I guess the challenge I'm really interested in is how to deal with the complexity of social situations, like when you have like a couple of people and you're not quite sure what they mean and what they want. So we have this picture that we took with one of my students a while ago, and it was a bunch of students in a student residence. They were playing some game together, and I love this picture because you have those three ladies and with completely different facial expressions. And as humans, we are pretty good at guessing what's going on. Like you have that person completely on the right. She seems to be speaking, like she's like using this kind of gestures to support her speech. That lady in the middle with this face that seems to be kind of half joking, like not really agreeing with the first one, but still kind of engaged. And the last one on the left, she seems to be a bit puzzled, maybe less engaged. I don't know. This picture is really so telling of real world, the kind of real world dynamics that we see amongst humans, and it's actually really hard to model that for our robots. It's subtle, it's ambiguous. There is all this group knowledge that is maybe not present. Like I'm showing you this picture, but we can easily infer that there's at least another person. Those people seem to be talking to another person that is outside of the field of view of the camera right now. So it's not just about like doing like end-to-end training on that image. You have to understand the context of the interaction. So all that makes the problem really challenging. On the other hand, we also it's obvious that the future of these interactions. I mean, we've heard what Carolina has been doing at Google over the last 2 or 3 years. It's really impressive. So it's obvious that the future of our interaction management generation is going to rely on LLMs in particular, or like multimodal, like VLMs, things like that. So my question was really how to bridge the two. How can we provide an input to those machine learning algorithms that would model what I'm calling here the social sphere, like the social environment. Just going end to end is difficult because it's very multimodal. It's very dynamic. You cannot look at one snapshot. You need to have like the history of the interaction. You need the context of what's going on. If we know that this picture was taken in an evening in a kind of a board game situation, that tells us already a lot of background knowledge. And also end-to-end learning is kind of difficult for a company like Power Robotics because it's not makes like explainable AI much harder, and a robot is not there to just like do one task. There's a lot of processes going on, so we need to have a kind of a high-level robot controller that is going to take maybe the LLM input or maybe the task planning, the LLM-based task planning as one input for a final decision that will be made outside of the LLM. So the idea is maybe what we need is some sort of social embedding, a way of compactly represent complex social situations. So how can we do that? How can we represent social scenes? We started last year to play a little bit with those very simple simulations. So we built this little simulator with little characters moving around. So I don't know if you can see the arrow, like that character here is kind of moving forward. There's two people chatting together. And the question we were asking is, okay, I show you 3 scenes, A, B, C. Which ones are most similar? Which one in social terms? Which ones are the most like the most similar? And okay, in the first situation, you can see someone walking toward the robot and 2 people chatting together. In this situation, there's like 3 people having a chat, another person walking toward the robot, and then a 4th person just passing by, or 5th person passing by. And in this last scene, the scene C, you have like still 2 people chatting together, 1 person actually chatting talking to the robot and another person just walking away. So as social beings, for us, it seems quite clear that situation A and B are closer to each other. Like they like a group of people chatting and one person trying maybe to interact with the robot, moving toward the robot. While the scene C, we are already in the interaction. So the intuition of social embedding is to say, okay, fine, can we model a scene like that as a vector, A, B, C, each scenes get their vector. And if we do that, then in principle, if we build our embeddings properly, then computing the distance between those scenes, so some sort of social metric, how close, how similar two social scenes are, could be as simple as computing, I don't know, a cosine distance between two vectors. So for instance, here we could get like a cosine distance of 0.12 between A and B. That would be smaller than the cosine distance between B and C. And we could say, okay, brilliant, B is socially more similar to A than to C. Now, how to do that? Like we've been looking into that for a long time, and it's difficult. Like it's very multimodal. Do we track the bodies, the face, the gaze, what people are saying, who is speaking, the direction of like the relative position of each of the actors? It was not obvious how to build those social embeddings, and the insight that we got last year was to say, okay, that's fine. If we are struggling to properly build do feature engineering on a social scene, let's go natural language and ask the LLMs, or more accurately, the embedders in the LLMs, to do the work for us. And then the problem is completely different. It's not anymore about building engineering features. It's just trying to creating descriptors to describe in natural language a scene. So 3 steps: extracting descriptors that might be, I don't know, John is talking to Rose, and Eddie is walking toward Jane, things like that. Then with those descriptors to build a description, and then to embed it using an off-the-shelf embedding algorithm like the one in GPT, like ADA2 or the Llama 1 or things like that. So it means that like scenes like that then becomes descriptions. A group of 2 people chatting, someone is walking toward me. B becomes in front of me, 3 people chatting together, someone is walking towards me. And C becomes I'm chatting with 1 person, another group of 2 people are discussing on the side. So it's actually not very difficult to generate descriptions like that. So we published a paper last year, very, very basic algorithm where we were just computing the distance between people, the direction of motion, whether or not they were looking at each other, to generate a description that sounds quite boring, but like Bob is not far from me. Emily is close to me. Emily and I are looking at each other. Bob and Will are looking at each other. Will is talking. Emily is talking. Bob is looking at me. The names here are completely random, and we actually we actually played in using different names. It does not matter. The reason why we are using names, actual human names instead of just letters, for instance, is because the underlying idea of using an LLM to build the embedding is to exploit the social knowledge that is in the latent space of the embedding of the LLM. And our hypothesis or our intuition was that by using actual human names, we are making the life a little bit easier for the LLM. We are already grounding our text into social scenes that involve human beings. So we did that. So those 3 scenes get their automatically generated descriptions. And then we started to look at the end. So we ran that through an embedder. So OpenAI ADA2. Actually, all the results I'm going to show you come from ADA2. And we get those embeddings. Now, how good are they? I did mention previously the idea of a social metric. Can we use to compute how close the scenes are? But maybe just before looking into that, the first question was, okay, are we actually encoding the semantics of the social situation and not merely the like the strings, like the syntactic structure of the sentences? So we ran a very simple first analysis. So on those 2 graphs, the there's like a shaded area, and there's a line. And the line actually, so we extracted 90 situations, 90 situations like those ones, generated the embeddings for those ones, and computed the pairwise distance in the embedding space between all those situations. And you can see that, so that line here is the distribution in the embedding space of the distance between those scenes. So some seems to be very close to zero. So some of those scenes were embedded in a way that were very close to each other, and some were further away. In the textual space, so we took the strings, the description directly, and we computed the Levenshtein distance. And you can see that distribution of the Levenshtein distance, same thing that just the line. So that gives us an idea of how those 90 situations were distributed in space, in the textual space or embedding space. And now the shaded area represent, we took one single scene, and we generated one variation, like we randomized that description by doing something very simple. We just changed the order of the descriptors. So for instance, Bob is not far from me, Emily and I are looking at each other, Will is talking, Emily is talking, becomes Emily is talking, Bob is not far from me, Will is talking, Emily and I are looking at each other. So it should have the exact same semantic value. We have just changed the order of the sentences. And so we re-embedded those variants to see if I like a reference scene and with a reference description and a variant of that scene would end up very close in the embedding space. And that's what you see here. So it's not perfect. Ideally, we would want to have everything on 0 because the semantics are the same. But we can see that the distribution of those semantically equivalent descriptions is much closer to 0 than the generic distribution, the overall distribution of the social scenes. While, and it's not very surprising, if you look at the Levenshtein distance, then the distribution of the variance is actually spread over almost the whole range. Because of course, if you compute the Levenshtein distance, which is just like a string, like a character by character distance between the two strings, by changing the order of the descriptors, you completely mess up the things. So it seems that at some level, we are encoding the semantic, not just the syntactic structure. But now, what about the social metric, which would be really the big promise of those social embeddings, a tool to measure social similarity, to quantify, which would be completely new in the field of, like, for instance, sociology, where people talk about, like, okay, how similar those two scene situations are, but we don't have any tools to actually measure that, to quantify that. So if we were able to do that, that would be actually really, really useful, and also actually beyond social robotics as a tool for social sciences. So the question is then, okay, if two social scenes in the embedding space are close, small cosine distance, are they indeed socially similar? And then that immediately raises the question of, okay, but what does that actually mean to be socially similar? Currently, like until now, I've just said, okay, like people seem to be doing the same things, that must be the same situation, but in practice, it's more subtle than that. So the hypothesis, or the best case, is our social scenes are, once we embed them, they end up in a latent space that is structured as a metric topology. By metric topology, I mean the distances between two scenes. So if A and B are close, then B will be, and B is far from C, then A will also be far from C. And hopefully that rings a bell in your mind immediately, because what I'm describing is basically the definition of a metric. And a metric, as you might remember from a long time ago when you did a bit of math, I had to check on Wikipedia, to be honest with you. A metric, an operator is a metric if the distance to itself is 0. So that comes naturally from the cosine distance. Like if you compute the cosine with the two same identical embeddings, you'll get 0. It needs to be, there's the criteria of positivity. If two things are different, then the distance has to be different. That will be the case. We will get two different embeddings, and the cosine distance will be above 0. It has to be symmetrical. So the distance between x and y is the same as the distance of y and x. That comes automatically from the cosine distance. But the last one, which is the most important one, is the triangle inequality. So the distance between X and Z has to be smaller than the sum the sum of the distance between X and Y and Z. Basic geometry. Now, is our social latent space in the LLM latent space, is it a space that is actually a metric topology? And that would mean that inequality is verified. It might well be the case that the topology, the latent space topology, is actually not, has a weird shape that we don't really understand, and I don't know much about it. So that's really clearly something that we need to investigate more. We simply did some empirical experiment where we randomly picked triplets of scenes that some of the scenes I did show before. We computed their distances, and we were able to verify that out of 1,000 randomly picked triplet of scenes, the triangle inequality was verified 96% of the time. So it's not quite enough to be a metric. Maybe if we are very, very kind, we can call it a quasi-metric. It might be a matter of creating different prompts or different description of the scene, or fine-tuning the model. We don't really know, but clearly we are close to it. And if that's the case, then that's amazing. That really, we are really showing that maybe social embeddings, something as simple as describing and then using an LLM to create an embedding, might be sufficient to quantify how similar social situations are. I'm going to skip that, but we tried to actually run an online study where we asked humans to rate how similar scenes were, to compare this kind of ground truth of social similarity based on human knowledge to what our model or our social embeddings were able to give. And very, very briefly, in roughly 2/3, like 65, 62, 66% of the cases, the social embeddings were able to rate or to consider that scenes were more similar to each other, the same way humans would consider two scenes to be similar to each other. So it's not quite good enough, but there is maybe something there. Okay, I'm jumping to maybe one example of using that is actually quite interesting. It's about interpreting expressions in context. So you remember that that first picture that I did show, we had those very complex subtle expressions. What if now we use, instead of just using LLMs, we use VLMs, and we ask, for instance, in that case, GPT-4, the vision model of GPT-4, to describe the facial expressions of people. So we extract them from two different data sets. One that was like a standard data set on emotions that has like a lot of faces that are showing a neutral expression, and then one of the standard happy, sad, disgusted expressions. So we have like a reference frame, reference face, and an expressive face, and another set of faces that come from a more naturalistic data set that we acquired in a library, where we were running an experiment with a robot that was on purpose misbehaving to generate a range of facial expressions. What was interesting is to see that a model like GPT-4 is actually really good at picking up really kind of subtle cues. So if you take the first two pictures here, between the first two, we did send that to GPT, and we asked, okay, can you describe the expression on the second picture? So, and then the GPT says something like, the person appears to have a more serious or concerned expression with a slightly furrowed brow and a closed mouth. On the second one, the person appears to have a neutral expression with a slight frown. The third one, the person appears slightly more concerned or confused with eyes slightly widened and eyebrows raised. That was really impressive. Like, it's, I mean, compared to the standard emotion recognition modules that are running usually on our robots that just gives you, 70% happiness and 20% sadness. Those are much more subtle and actually accurate descriptions of the expressions. But now the interesting thing is the context. I just put that example here. Like, okay, I'm a waiter robot telling a joke to entertain the customers. Bob is looking at me and Bob is laughing. Okay, seems to be congruent, seems to be appropriate. While if my current state as a robot is, I'm a waiter robot taking orders, Bob is looking at me, Bob is laughing, even though that the same social scene description, because of the context, I can say that this second example, something wrong happened. That would be great if our LLM, if our social embeddings were able to also model the context. So that's what we tried to do. So we took those two pictures. So I told you the MMI data set where we have those two faces, a neutral and then with an expression. We asked GPT to describe that transition. So this person is showing a more amused expression with a slight smile. And then we also generated the embedding of two what we called reference points. And those admit that it's simply the embedding of the sentence. This is an appropriate interaction for the positive reference point, or this is not an appropriate interaction for the negative reference point. So we embed those three sentences, 1, 2, 3, and we simply, it's very simple, compute the distance between the expression to the first one or to the second one, and we look at which one is closer to the other. It's if you just do that with the raw data set, no specific context. So we just do exactly that. We ask GPT-4, sorry, to generate the descriptions, and we compute how close or far they are from the positive or negative reference point. You get something like that. So in the middle, at 0, 0, that would mean like an expression that is completely equidistant in the embedding space to both the positive, the appropriate interaction, and the non-appropriate interaction. And on this basic first attempt, we can see that the happiness expression is way closer to appropriate, and the sad expression is definitely in the more negative space. Things are more messy with expressions like disgust, for instance, that are a bit all over the place. But for happy and sad, it's quite clear. Now, if you do the exact same thing, but you add a bit of context saying, you are giving bad news to a person, and then you add that context to the sentence. So you are giving a bad news to a person. This person is showing a more amused expression with a slight smile. Then it's not completely surprising. But in the embedding space, suddenly having a happy face goes down massively, while having a sad face goes up massively. So we are kind of showing that using those social embeddings, we are able to measure social congruence, whether or not an expression is adequate, appropriate, not only in general, but also in a given context. So I'm going to stop here. Last slide to explain why I think this is quite exciting. I think that's a really novel way of doing social situation assessment. So we can now, we have a tool or an initial tool. There's still a lot of research to be done, but to compare social situation and quantify how similar they are. We can also think of using it the other way around to retrieve situations, saying, okay, I'm seeing that situation now. What other situation I know that were similar to that, and what did I do, or what happened in those previous situations that I need to know to correctly behave this time? We are able to easily model context awareness, which was until now extremely difficult to model in social assessment. There's one thing that is potentially extremely exciting is this idea of social dynamics, because social dynamics, looking at how a social situation evolves, once you reason about that in the embedding space, it becomes really trajectories in the embedding space. So each of your social scene situations becomes point in the embedding space. You can look at that trajectory, look in terms of look for discontinuities, for instance. Oh, there's suddenly a really big change in the social scene, so maybe I need to do something about that. And you could also potentially predict the social scenes by simply extrapolating those trajectories, which would be actually really interesting to look into. And potentially, we have a tool that could become a really interesting input for more traditional machine learning, for potentially LLMs, or for more fine-tuned models that would take the social scene as an additional input. It's not completely clear, so let's have maybe a brief discussion if we still have time. Using LLMs to generate social embeddings, that might feel like a cheap trick. It's just, writing a small description that is actually really simple, and then using the embedder coming with the LLMs to generate my embedding. But actually, it's maybe not such a bad idea in the sense of we are using natural language as a bridge between a lot of different modalities. using natural language with all this, built-in ambiguity and precision is actually pretty efficient to describe social situations that are themselves pretty ambiguous, complex, unclear. It's also, of course, a great way of exploiting the latent representation of social norms, social know-how that we already know has been encoded, is present in the LLMs. And it's also extremely easy to extend because it's just about generating a description of a scene. So as long as you're able to describe, I don't know, a facial expression, you can add that to your scene description. If you're able to describe the gestures, recognizing gestures, Jack, you can refine the description of the scene. And at the same time, there is a lot of things to still understand model about the latent structure. We are relying on our intuition that the topology, the latent structure of the LLM is actually suitable for this kind of reasoning about social similarity. It's based on the intuition, some data, but not yet grounded into any formal theory. So I'm going to stop here. Thank you very much, and I would be more than happy to take questions.
Thank you, Séverin. I don't know if you can hear me.
Yes.
Yeah, thanks for a great talk. So one thing here is, I wonder if VLMs and LLMs may always contain all this social knowledge that you are trying to encode here, especially for contexts that require fine-grained information that maybe cannot be expressed in language. For instance, like close relationships or the context of people. And so I'm wondering if you have encountered some limitations on LLMs as to extract these representations, and whether you think that there's ways to mitigate those, whether to learn with robot data or there's other sources that we could get these embeddings from.
I mean, it's a really good question. I need to be completely honest. We are only at the very beginning of that. So we've worked mostly on this kind of very artificial, scenes. We did run the whole system on the robot as well with actual detection of people to see how it behaves. But the level of modeling that we are doing, the complexity of the descriptions we are generating is still very, very basic. It's actually very similar to the example that I was giving there, where you have really just describing how far people are from each other, who is talking, who is walking in which direction, things like that. I have the intuition, and I think it's an intuition that is shared by many people who have been playing with LLMs on social interactions over the last 2-3 years. That LLMs are actually really good at modeling actually pretty subtle, pretty complex human relationships, probably just simply due to the fact that there's so many examples of that in the texts that are online, in the literature, in the web content, social media, things like that. That I have the intuition that the bottleneck is not going to be so much the ability of LLMs to model and represent and reason about complex social relationships, but I don't know is the short answer. We haven't really tried that yet.
Thank you very much.